Welcome to Cracking Cancer, where we tackle the tough questions about cancer with real patients and world experts. Our mission is to empower the cancer community through education, bring transparency to the oncology system, and drive funding for critical cancer research. Whether you're facing a diagnosis, supporting a loved one, or simply here to learn, we're here to bring clarity, hope, and action to the fight against cancer.
Can we go back to when you talk about the word mutation? I think that's a little bit confusing, or would have been confusing to me in the first place, because when you say mutation, I automatically go to those mutations that people recognize and can be targeted for different treatments. So like HER2, EGFR, ALK, specifically for lung cancer. And I know there's other mutations for other cancers, but it's not necessarily a mutation like that, correct? When you're saying the word mutation.
Yeah, there's a lot to unpack there. So I'll back up. So when we say mutation, what we mean is in each of your cells, there are, billions of individual pieces of DNA. And they have, one of a couple of options that it could be. Like your DNA has, essentially 4 choices of, it could be an adenine, it can be a thymine. If you remember from basic biology, which you've probably tried to scrub from your brain. But you can have an error there where one will turn into another one. So there's nothing inherently wrong about the piece of DNA, but keep in mind it's a template. So the template is now incorrect for the protein that you want to make. It's like if you're building a house and all of your walls are wood, but then one gets put up as, roofing. It's like, well, it'll technically still, like, these are still the elements of a house. It's just in the wrong order. Like, it's not going to function the way you want it to. So the mutation is an error in the DNA that will make a protein that doesn't do what it's supposed to do. There are many flavors of that. One flavor, and the ones that we hear about a lot, are these targetable mutations. When that happens, you get the proteins that have the divide signal. They have the potential for that divide signal, the signal that tells the cells to keep growing. And the mutation makes those just do that all the time now. We call that an activating mutation. For example, with Samantha, you have HER2. So there's a mutation in that protein that now tells the cells to just keep growing. It's not the most common cause of cancer to get one of these types of mutations, but when they do occur, they are often, not always, but often targetable. We can create mostly pharmaceutical companies create compounds, drugs, that can bind to that mutation, that protein that's doing, all this telling the cell to divide that it's not supposed to be doing. And since those cells no longer get that signal and they become addicted to that signal, the cells die. So that can kill off a good portion of the cells. On the other hand, for those who don't have these targetable mutations, where you had the error just telling the cell to divide over and over again from a single protein, a lot of times it's what we would call a cumulative burden or multiple hits. So an example there might be someone who smokes. They get the tobacco smoke comes in, it has a carcinogenic effect, meaning it causes mutations, but it's causing mutations throughout a lot of the cell's DNA. So when I was saying earlier, you have hundreds of these proteins that tell the cell to divide less and hundreds that have the potential to tell the cell to divide more. It's not just one or the other that happens. You get many that get mutated. And that's another mechanism where cells can become cancer. But since you have multiple proteins that are abnormal and it's not just one thing, we really struggle to develop thoughtful medicines to target that. And that's probably where a lot of people get this idea from that cancer is cancer because, and they're not unique diseases. Because before we had this understanding that sometimes a single mutation can cause cancers, the cancers functioned pretty similarly. And now that we understand that, we realize that they are different. But for those who don't have these targetable mutations, options are more limited than those who have these targetable mutations.
Yeah, I think the shock for me when I understood that cancer was more complex than I had ever known was when they sent my blood and tissue off for I don't know what the appropriate word is, but molecular look at what my cancer was made up of. I don't know outside of lung cancer if that's a common thing also now or not, but it is in lung cancer. And I would argue that my genetic profiling of my cancer, or whatever the appropriate term is, was actually pretty boring in the sense of I only had two things. I know other people that have like 30 mutational things that are going on. But again, just learning the different names of these different things that have gone wrong, it's just like, oh, wow. That's a lot of things that can go wrong. And for my case, it was only two, but for others, it's a lot. And it made me realize, okay, this really is a lot more complex than I ever thought. And I now drill down further and further and further and learn things I don't want to learn. But it's fascinating. Just like you can really drill down into this stuff and learn so much about where that error went wrong in your cancer. And maybe a lot of people listening don't want to know that, and that's totally understandable. Sometimes the things that I learn, I wish I had never learned. But it's interesting.
What would be an example of the kind of information about your molecular detail that you wouldn't want to know?
So there's a lot out there on Google, good old Google, blessing and curse, about TP53. So TP53 is a mutation, again, intercept me if I say this wrong, is a mutation that occurs in a high level of number of cancers across the board. But if you have a mutation like mine, I'm HER2 and TP53, it means that if you're targeting that HER2 specifically, you still have this rogue TP53 that eventually might overtake that HER2 targeting drug and be like, nope, I still want to grow and mutate and do my own thing. And so when you Google TP53 and other mutations, it'll be like, yeah, your prognosis is not as good. So that's just an example of not wanting to know the things that I read.
Yeah, I think that's a good example. That makes sense. And in your case, you had one of these mutations, that the HER2 mutation that tells the cell to divide.
Mm-hmm.
And with TP53, that's a mutation that actually inhibits the function of TP53, which was one of those proteins that tells the cell to not divide.
Right.
So it's kind of accelerating the cell's growth you took off the brakes and you pushed on the gas.
Mm-hmm.
I'll say also these molecular profiles that people get from either the tissue biopsy from the tumor, from the blood. What happens is we send those out for molecular testing, and they look at, actually, this is just a limited number of genes. So they'll look at, depending, 50 to maybe a couple of hundred genes, and they'll say, are there mutations in any of these? And there are tens of thousands of more genes that we're not mentioning. So there's a lot of information about one person's individual cancer, and the field is growing to learn more and more and more. And part of that's cost. Part of that is we get all this information about stuff that we can't act on, so it doesn't materially change someone's outcome in any way.
Just gives anxiety.
It just gives anxiety. And, I'll say from a researcher perspective, the more we know, the better, because we don't know necessarily how these things work together, how these proteins work together without studying them. But there's a lot of information about a specific tumor, and it can be very overwhelming. And if someone is looking into what caused my cancer and they get a list of 40 genes that come back as mutated, that's hard. That's hard for us to know what to do with. Sometimes we'll have a good sense, but not always. And for the person who has that cancer, if you're trying to make sense of that, that's going to be really distressing, I think.
Yes. Yeah, there's a fine line there. Very fine line. Um, can we talk real quick about, this might be the dumbest question I've ever asked ever, but I was thinking about it the other day, and so our audience might also be interested. So when you talk about like amino acids and proteins and things going wrong, etc. So as a prime example, I looked the other day and on my mushroom coffee ingredients that I drink, it's like a coffee replacement. And it said on the packaging, 30 amino acids, and it listed all the amino acids. And then I saw that, ironically, my mom picked up on this, that the amino acid that went wrong for me personally at my molecular level was listed on the mushroom coffee as an amino acid that you ingest. And so I was like, huh, that's interesting. And I know that that's not related per se, but like, can you talk a little bit about how the differences, I guess, of like us as a society ingesting like different amino acids and
Yeah.
from foods and products, and how, I don't know, is that is that the same protein as that went wrong in my body, like or not, or is it totally unrelated?
Yeah. When we get into what is cancer and what makes up cancer, I'll go back to the house analogy. You know, the parts of the DNA, the parts of the protein, all of that are okay. Everything's function, like all of the building blocks are the normal building blocks. So and for those who don't know, an amino acid is a small bit of protein. It's like one of the Legos that you would put together to make a full functional protein. So, and when a DNA is mutated, it says use this amino acid instead of this one. So you exchange out one Lego for a different Lego, and then your final construction is a little bit wrong. And that little bit wrong can actually have really, really big consequences if it's in the right spot. So here, your body needs amino acids to live, certainly. Those are the building blocks for protein. And there's nothing inherently wrong about the amino acid. It's where that cell told the body to put it. And if you have a normal diet, many of the amino acids your body's going to make on their own. So there's not a whole lot you can do. I would not deprive your body of the amino acid that is wrong, or put there wrongly, because if it's necessary, your body's going to need it for a lot of things. And a lot of them your body's going to just make anyway. But a lot of people do wonder, what are the things that I can eat? What are the, what can I do dietarily to change my diet? And we're going to have a full episode with a registered dietitian, because I am not. But generally speaking, there are not diets out there that I'm aware of that dramatically help someone's cancer once one's formed. So the cancer, by and large, is going to get what it needs. There is molecular data and data from outside the clinic, like in cell lines and mouse models, where we can play with these variables and get certain effects. But how that works in a human with a functioning GI tract and all these things is a much different story. So I think it's fairly easy to find some information online that's going to support whatever theory you may have. But once it goes to the patient, that is a totally different ballpark. And we've experienced that with drug development forever. Things look really, really good in cell lines and mouse models, and then they go into the patients and no effect. But when it comes to metabolism, a cell working on its own in a petri dish in a very controlled environment is completely different. It gives us some understanding about how cells might work, but it doesn't give us as much understanding about how to target cancer as we want.
Can we talk a little bit about what is cancer in terms of different age brackets? So I think it would be helpful for our audience to know a little bit about, like, okay, well, I got diagnosed in my 20s, or I got diagnosed as an 18-year-old versus someone who is 70 years old. Like, does that mean that did all the processes that you're talking about occur in the same way, like no matter what age you are? It just happened to occur at that age versus 60 years later for someone else. I'd love for you to go into that a little bit.
Yeah, there are differences molecularly that we see in patients who are much older and patients who are much younger. I think for the general audience, those don't move the needle much. Like
Yeah.
generally how cancers form is the same, how cancers are treated is the same.
Yep.
We might have slightly different regimens, particularly for children, than we do
Yep.
for adults, and younger people tend to do better. So that's another consideration.
Mm-hmm.
As people age, they have more opportunity to develop mutations. Their body has been exposed to more things, and the the error rate that you'll find in DNA for older patients is higher than younger patients in general.
Gotcha.
But the way the cancers form, behave, and are treated is similar.
Okay.
So far we haven't identified something that we can act on
Mm-hmm.
in a young patient versus someone who's older that will change therapy in any meaningful way yet. That might
That's
come
super.
out, but
That's super helpful because I, again, like as a 37-year-old being diagnosed, I'm like, okay, well, did this all occur in a perfect storm? Clearly, very differently to someone that was diagnosed when they're 95 years old. But like you said, cancer is cancer. Like it forms how it forms, and it is the same. It does not discriminate, no matter what age you are, and that is the process of cancer.
yeah. And if you were entering into my office as someone who's 90 versus someone who's 30, and you both have this HER2 driven cancer, the mutation in your example, my talk would be the same. Of what caused your cancer would be this mutation. How it got there would probably be pretty similar in terms of my thinking, but someone who's 90 had probably more opportunity to develop that. Yeah, that's my thinking. Although people are doing more research into how the body copes with mutations over age, and we're just not there yet in terms of better understanding that and seeing if there's anything we can do. Because most cancers don't occur young. Most cancers do occur as we age. So, you know, is there more to that than just there was more time? So you had more opportunities, or do these processes change like your ability to fix mutations, to clear one tumor cell that's abnormal. The immune system can clear those things. We know immunities change over time. There's a lot to unpack, and the field is still young. Thank you for joining us on this episode of Cracking Cancer. If you found this helpful, please like, subscribe, leave us a review, and visit crackingcancer.org for more information. Every dollar we earn goes directly to furthering the podcast and supporting vital cancer research, because together we can crack cancer.